So to finish this chapter on indices and logs, we're obviously going to look at logs, okay, logarithms as they're called. And the reason why we look at logarithms and indices in the one chapter is for a reason that we would have met in the chapter on functions. And that is the following. Watch. If I take an exponential function and a logarithmic function, both written to the same base, okay, and I was to plot them on the xy plane. Now, we already know from a previous chapter on functions that exponential functions, they kind of creep up gradually first and then all of a sudden they explode, okay? Logarithmic functions, on the other hand, increase rapidly and then tailor off. So you get something like that, okay? So this one here would be your log function and this one here would be your exponential function. Now, remember what we did in relation to inverse functions in the previous chapters. We all said that if you take a line y equals x and run it through a pair of functions, and if the functions are symmetrical about that line y equals x, then those functions are, if you can remember, inverse. Okay, so straight away there's your proof that exponential functions and logarithmic functions are inverse to one another. Okay, and the lovely thing about that, and we'll find out towards the end of this section on logarithms, is that they can be used together in order to simplify a whole range of complex equations and complex situations. But we'll deal about that when we get onto it. Okay, so log functions are the reverse process or inverse of exponential functions. I want you to consider these two forms. 2 to the 3 equals 8 and log to the base 2 of 8 is equal to 3. Now, they basically say the same thing, okay? But they say it forwards and backwards, for want of a better way, or forward and inverse, forward and reverse, whatever way you want to say it. And I'm just going to take it through their structure, through their form. If you take the first one is obviously an exponential function. The second one is obviously a logarithmic function, okay? Now, in this case here, let's look at the exponential function. What is the exponential function telling me to do? It's telling me to take the number 2, which is the base, and multiply it by itself 3 times. So 2 2s are 4 times 2 is 8. Okay, so therefore an exponential function will tell you how many times you multiply a base number by itself. On the other hand, the logarithmic function asks you how many times you're going to multiply a base number by itself to get a certain result. Okay, so in a situation like this, the way in which I would read the first half, the left-hand side of this equation, is as follows. Log to the base 2 of 8. Now, what is the logarithm asking me? The logarithm is asking me how many times do I multiply 2 by itself to get 8. So you take the two numbers that are side by side. How many times do I multiply 2 by itself to get 8? Now we've got the answer over here already. If you multiply 2 by itself 3 times, you get 8. So therefore the answer to this logarithm is 3. So what does an exponential function tell you to do? An exponential function tells you to multiply a base number by itself a certain number of times. What does a logarithmic function ask you to do? It asks you to find out how many times you're going to multiply a base number by itself in order to get a certain result. And the two numbers that are the base and the result are the two numbers that are in the logarithm. Log to the base 2 of 8 means how many times do I multiply 2 by itself to get 8. Okay. It is important to note that we always use positive bases with logs. Now it's amazing the number of people who do logarithms and don't realize that 0 can never be a base for log, okay? And also -1 can never be a base for a log. And here's the reason why. The reason why it cannot be, 0 can't be a base and -1 base is because they cannot be bases in index form. They can't be bases in exponential form. And what do I mean by that? If you take 0 to the power of 0 and you put it into your calculator, syntax error. Meaning what? Meaning that 0 cannot be used as a base, because we know that if you take any other base and you raise it to the power of 0, you're going to get 1, okay? And also, if you take -1 and raise it to the power of a half, what you're asking is what is the square root of -1? And again, if you ask your calculator that, it'll give you a syntax error, even though I suppose we know in complex numbers that the answer to that is I. But for the moment, the square root of -1 in real terms can't be found. So 0 and -1 as bases cannot provide us with real results. So therefore what we say is that when we're using bases or using logs, the base number should always be something that is greater than 0. Can't be 0, can't be negative, so therefore anything that's positive and is greater than 0 itself. Therefore, a to the power of m equals n is totally interchangeable with log to the base a of m equals m. Now, let's see again. This is the exponential function. There's the exponential function. There's the logarithmic function. Exponential functions tell me to do something. Take a and multiply it by itself m times to get n. Whereas the logarithmic function asks me, how many times do I multiply a by itself to get n? And the answer is m times. And that's why the answer to the log is m, because that's the number of times I'm going to multiply a by itself in order to get what n, the object that I'm getting the logarithm of. You must be able to move freely between index and log form using that identity. Okay, a to the m equals n, log to the base a of n equals m. Now here's what I want to point out to you. The nice thing to remember about changing form between exponential and logarithm form is this. In the exponential form, the base on the left hand side is a. In the logarithmic form, the base on the left hand side is a. So therefore, whatever the base is in index form will also be the base in logarithm form. And likewise, vice versa. Whatever is the base in logarithm form will also become the base in exponential form. And that's always going to be your starting point. What is the base of the index, or what is the base of the exponential form? And if you know, say the exponential form, you want to go into logarithm form, you start with the base. So example, write log to the base 4 of y equals 3 in index form. What is the base of the logarithm on the left hand side? The base of the log is 4. So therefore, the base of the index form will be 4. Logs always reveal powers. See that? And I want you to remember that logs always reveal powers, like that. So therefore, the power that's going to go over base 4 in index form is 3. And that is equal to the number that I'm getting the log of, namely y in this case. Look at it again. Log to the base 4 of y equals 3. Write it in index form. Okay, what's the base of the log? The base of the log is 4. Therefore, the base of the index form will be 4. The log reveals the power. So therefore, if 4 is the base, 3 is the power. And lastly then, when you've put the 4 and the 3 together, obviously on the other side of the equation will be y. And if we were asked to solve this, we could simply say, well, hold on a second, 64 is equal to y. Because 4 by 4 is 16, by 4 is 64. Okay. Write x to the power of 5 equals 32 in logarithmic form. Now, can I go from index form to logarithmic form? Yes, using the same starting point. Take your index form. What is the base on the left-hand side? The base on the left-hand side is x. So in logarithmic form, the base of the log will also be x. The log reveals the power. See that? The log reveals the power. Now, what's the power over here in index form? 5. So the log reveals the power. And the last thing I've got to do then is take the number that I have as a result of the exponential form into the space that's left. So log to the base x of 32 is equal to 5. Now you have to be able to do that almost in your sleep. You've got to be able to do it extremely freely, because sometimes they'll give you a logarithm that you can't work out in that form, but as soon as you put it into exponential form, it works out lovely. And likewise, sometimes you might have an exponential form that you can't use properly, but when you put it into logarithmic form, the answer falls out nicely. So as I said already, logs will tell us how many times a number is multiplied by itself to give a certain result. Now look, there are 4 scenarios in terms of being able to use logs, okay? And I'm going to do an example of each of the 4 of them here. The first one is where you have the base smaller than the number that you're working with. So if the base is smaller than the number you're working with, well then that means that the answer to this thing is definitely going to be greater than 1. Okay, simple as that. In order to get 5 up to 625, you're going to have to bring in a power that's obviously greater than 1. So therefore, ask yourself a question. How many times is 5 multiplied by itself to give 625? So let's have a look at that. 5 by 5 is 25. By 5 is 125. by 5 is 625. So therefore, in order to get 5 up to 625, we need to raise it to the power of 4. And that is the answer to log to the base 5 of 625. The answer is 4. Okay, next one. What happens when the base is bigger than the number you're working with? Now, in a situation like that, you're bringing the base down, okay? And if you're bringing the base down, then obviously the power you're going to be dealing with is going to be less than 1, which means the power is going to be fractional. So now I've got a situation where I want to bring 121 down to 11. And here's what you got to ask yourself. What power do I give 121 to get 11? So what I'm going to do here is I'm going to write this in index form first of all. The base of the log is the same as the base of the index, okay? The log is the answer, so therefore we don't know what the answer is just yet. And then we're told that we have to get, 11, isn't it? Yeah, apologies. Is it 11? Okay, so 121. The log of the number we're dealing with, that's equal to 11. Now, what do I do to 121 to bring it down to 11? What do I do to 121 to bring it down to 11? And I hope you can see that the square root of 121 is 11. However, square root symbols, as we already know, are symbols and can't be used as symbols. So instead, we use the power of a half. And there's your answer. The answer here is a half. Okay, so let's just go through those again. When you're bringing the base up to a bigger number, the answer is going to be greater than 1. When you're bringing your base down to a smaller number, the answer is going to be less than 1. Indeed, it's going to be fractional because it has to be between 0 and 1. So it'll be a fractional answer. And in this case here, what power do I give to 121 to bring it down to 11? And the answer is obviously a half because it's a square root. Next one. What happens if you're getting the log of a fraction? Now here's where we've got to fall back on something that we already know. 1 over 81. I want you to think about 1 over 81. That is what? That's 1 over, what's 81? Can I rewrite 81 in terms of the power of 3, or in terms of, base 3? So log to the base 3 of 1 over 81. What am I going to do with that? Well, first of all, let's just look at what 81 is. 81 is 3 by 3 by 3 by 3. 81 is 3 to the power of 4. See that? Now, here's another thing you also know from the previous section on indices. When you have a denominator that contains a power, then you have a negative index. Remember I told you that? Negative indices form fractions. And likewise, say that backwards, fractional indices, or I should say fractions with indices in the denominator, come from negative powers. So therefore I'm going to rewrite this as log to the base 3 of 3 to the minus 4. Now, here's the next thing. And this is a rule that I'll be coming on to in a few minutes. There's no harm to introduce it now. When the base of the log and the base of the index part are the same. This log has base 3, this index has base 3. So when the log has base 3 and the index has base 3, the answer is just the index. Okay? So watch that rule very carefully. It's a lovely way to remember that logs and exponents are inverse functions of each other. So log to the base 3 of 3 to the 12 will be 12. Log to the base x of x to the 7, 7. If the base of the log and the base of the index happen to be the same, then they're inverse functions. They will cancel each other out and you'll be left only with the index that was over the original base. Okay. And lastly, what is the log to the base 5 of 0.0016? Now, the first thing I want to do with that is I have to get 0.0016 into some type of relationship with base 5. Okay, and I don't know whether your calculator will do it or not. If you put in 0.0016, let me just check this now and see if I've tried this before. Will it do it? Oh, well, yeah. Your calculator tells you the following, all right? If you tap in, let me just get rid of all that writing up there. If you tap in 0.0016 on your calculator and press equals, 1 over 625, okay? Now, can I write 625 as 5 to the power of anything? Well, 5 5s are 25. Times 5 is 125. Times 5 again is 625. So in other words, 625 is 5 to the power of 4. Meaning, and this goes back to indices, 1 over 5 to the 4. If your denominator has an index, well, then you can write that as a negative index, meaning 5 to the power of minus 4. So I can now rewrite this as log to the base 5 of 5 to the minus 4. Check the log. What's the base of the log? 5. What's the base of the index immediately after the log? 5. Log with base 5 and the index with base 5, just leave the power, and again the answer there is minus 4. So you've got to be very careful that 0.0016, it's of no use in that form because it's not related in any way to 5 to the power of anything. Okay, so in order to get the two of them related, you take the 0.0016, tap it on the screen here, calculate, press equals, and it tells you that 0.0016 is 1 over 625. 625 is related to base 5 because 625 is 5 to the power of 4. And because 5 to the power of 4 is a denominator in a fraction, that index there will become negative 4, 5 to the power of minus 4, and you set that equal to 0.0016, or I should say you put it in for 0.0016, and you get log to the base 5 of 5 to the minus 4. Log to the base 5 cancels with base 5 and gives you the answer of minus 4. So just to run through those again, they're the 4 scenarios. They're the only 4 scenarios that you can actually have with straightforward calculating logs. If the base is smaller, if the base is smaller than the number you're working with, then that means your answer is going to be greater than 1. If the base is larger than the number you're dealing with, well, then you're going to have an answer of less than 1. If the number that you're getting the log of is less than 1, then that means that your answer is going to be negative. Okay? And finally, if the number that you're working with doesn't bear any resemblance to the base of the log, you've got a little bit of work to do to turn that 0.0016 into some type of relative in relation to base 5, which I did when I used 1 over 625. Of course, in the exam, you're allowed to use the calculator. There's no reason why you simply can't tap those onto your screen and press equals and get the answer. You're free to do that. But it's just nice to know how they work and what to expect when you're doing these things along the way. Just like indices, we have a number of rules to use when we're working with logs. Okay, now they're on page 21 of your tables and they're in the middle. So you've got the first column on the left hand side, which is your indices. Then you've got the middle column, which happens to be your logarithms. And I've kind of gathered them. There's about 6 or 7 of them in the tables. I've gathered them into 5 important ones that are the ones that come up most often. Okay, and again, there's a little bit of a kind of an echo here between the logarithm rules and the indice rules, as there should be, for the very simple reason that logs and indices are inverse functions. So you might hear kind of the echoes of what we would say are the principal rules of the indices. So take the first one. If you're getting the log of a product, because multiplication is related to addition, you may simply give the log to both parts of the sum. So what I mean by that is if you had log to the base 2, let's say, of 32. Okay. Now, just as a matter of interest, you could also say, well, hold on a second, 32 is 4 times 8. Now, that means that I could say log to the base 2 of 4, and because it's multiplication, plus log to the base 2 of 8. This is easy. How many times do I multiply 2 by itself to get 4? Twice. How many times do I multiply 2 by itself to get 8? 3 times. 2 and 3, 5. So it works. Okay. So therefore, the log of a product is equal to the sum of the logs of the individual parts of that product. Okay, next one. What about the quotient rule? The fraction. Fractions are division. Now, if multiplication is related to addition of logs, then division is related to subtraction. So if you're getting the log of a fraction, you may distribute that log to top and bottom and subtract log to the base a of x minus log to the base a of y. So again, if I'm asked what's log to the base 2 of, again, I'm going to take something very simple, 32 over 16, let's say. Okay, what do? The first thing I can do is I can distribute that log to base 2 to both of these, and because they're being divided, they will end up giving me a negative. Log to the base 2 of 32 minus log to the base 2 of 16. Now, how many times do I multiply 2 by itself to give 32? 5 times. How many times do I multiply 2 by itself to give 16? 4 times. Answer, 1. Okay, so the rules are nice to know. Again, if you want to use your calculator, but the rules are nice to know. Next one is a lovely way to get a difficult log simplified. So this is a kind of a simplification rule. If you're being asked to get the log of any term with power, the key thing to do is to take that power and bring it down to the front as a coefficient. So let's say, for example, I was asked to get log to the base 7 of 49 to the power of 4. Okay, now here's the key thing. If you're getting the log of a number with a power, the power can come down as a coefficient. So it becomes 4 times log to the base 7 of 49. And you ask yourself a very simple question. How many times do I multiply 7 by itself to get 49? So the answer there is 2. So I end up getting 4 times 2, which is 8. Okay. Now the more we see these things in practice, the more we'll understand how they operate. It's a little difficult when we're doing the rules because we're kind of doing them cold. But when you see them being done in questions, you'll get the idea. And the most important one, the one that really helps us to get out of a very sticky wicket, is this one here. What we call the change of base rule. Okay. Now, sometimes you might have, say, log to the base 4 of 32, and you want to change the base. Actually, just some here. Yeah, I'm going to write that. Okay, do that again. Pen. Okay, so you want log to the base 4 of 32. Now, problem. How many times do I multiply 4 by itself to get 32? You can't. 4 multiplied by 4 is 16. Multiplied by 4 is 64. So there is no index over base 4 that will give me 32 exactly. But if I drop the power, or the base I should say, down to base 2, this thing can be solved. Watch. Log to the base 4 of 32. Can't do it. So what do? I'm going to change the base. Now, what does the change of base rule tell me? The change of base rule tells me that if I want to change the base from A to B, I'm going to end up with a fraction. So every time you want to change the base, you're going to get a fraction. Simple as that. Okay. Now, what's the numerator and what's the denominator of the fraction? The numerator is simply the log rewritten with the new base. So I want to change this to base 2. So I'm going to write down log to the base 2 of 32. See that? And then what I do is I use the new base with the old base. Log to the base 2 of 4. Okay, so watch it again. Log to the base 4 of 32. Can't do that. So instead what we're going to do is change this to base 2, because there is a relationship between base 2 and 32. So you rewrite, every time you change the base, you're going to get a fraction. So you rewrite the log with the new base. So log to the base 4 of 32 becomes log to the base 2 of 32. And then you divide it by the log of the new base with the old base. That's what gives us that conversion. So what do I end up with? 2 multiplied by itself how many times gives 32? 5. 2 multiplied by itself how many times gives us 4? 2. 5 divided by 2, 2.5. There's your answer. Okay, so it makes life much, much easier if we can move away from bases that are difficult into bases that are easy. And in most occasions, and I say most, not all, the change of base is normally from a higher one down to a lower one. All right, that's normally what we're doing in a situation like that. And the final thing then is the equality rule, which is perfect logic. If log to the base a of x is equal to log to the base a of y, what do we notice? Just take a look at that for a moment. What do we notice? Look at both sides of the equation. Log a is common. You've got a single log on the left, a single log on the right. Both of them are log to the base a. Cancel, cancel. What does that give you? You just deal with the algebra. X equals y. Okay, so which one of those 5 would be the most important? The answer is the change of base. And after that, then you would have the power rule. So those two, you're going to look for them continuously as we go along some questions. So let's just do that. Let's hit some questions. Evaluate the log to the base 16 of 64. Now look, I could do this in a number of ways. Okay, is there a power that I can raise 16 to get 64? The answer is no. Is there a power that I can raise 4 to in order to get 64? The answer is yes. So what I'm going to do, the base on the log is too big. So I'm going to bring the base down. And I'm going to bring it down. I'm going to change to base 4. Now, here's how I use my change of base rule. Watch. I first of all realize that when I want to change my base, I'm going to get a fraction. On the numerator part, the top part, I simply rewrite the log with the new base and then log to the base 4 of the old base. See that? So log to the base 16 of 64, change the base, forms a fraction. On the top it becomes log to the base 4 of 64, and on the bottom it becomes log to the base 4 of the old base, which was 16. And now I can do this. How many times do I multiply 4 by itself to get 64? 4 4s are 16. 16 times 4, 64. 3. How many times do I multiply 4 by itself to get 16? 2. Answer 1.5. That's it. Done. That's all you've got to do. All right. Change the base if the base you're using doesn't suit you. Simple as that. If log to the base 10 of 3x plus 1 is equal to 2, find x. Now, here's the first thing we notice. X is trapped in a logarithm. All right. So what I'm going to do, because log to the base 10 of 3x plus 1 can't be done, I'm going to move away from log form into index form. I'm going to use the very, very first identity that we learned when we looked at logarithms. How do I change from log form into index form? So let's take this. Let's write it in index form and see, is it any easier to do? And here's what I need you to remember. Go over here, go to the left-hand side. What is the base of the log? The base of the log is 10. Okay. The log reveals the power that will be on that base, 2. And that is equal to the algebraic part, 3x plus 1. 10 squared is 100. 100 equals 3x plus 1. What does that mean? 99 equals 3x. So x equals 33. Okay, so you're dealing with algebra more so than you're dealing with anything else. You're going to use the rules of logarithms to get us out of sticky situations that are difficult to deal with when we don't know what the number is that we're trying to find the log of. So what do? Come out of log form, go into index form, and see if the index form is any easier. So don't be afraid to do that. And don't be afraid to test the rules to see which one works best for you. Next one. Log to the base 2 of x plus 3 equals log to the base 2 of x minus 9 to be squared. Now, first of all, single log, single log. So once you have a single log on both sides, you can then check and see, is the base of the log the same? And in this case, yes, on the left-hand side, log to the base 2. On the right-hand side, log to the base 2. So what do? Cancel them. And what are you left with? Just the algebra. X plus 3 equals x minus 9 to be squared. So you end up with x plus 3 is equal to, now square this thing out here, x squared. That's the first term. Take the minus 9, square it, plus 81 is the last term. And to get the middle term, minus 9x times 2 minus 18x. Okay, bring them all together. X squared. I'm going to remove x from this side and remove x, so that's minus 19x. And then I want to take away 3 from both sides, and that will give me plus 78. And that's equal to 0. Okay, now open your brackets. Let's see if you can work out what the factors are going to be first. Now 78 with a difference of 19 between them. So divided by 6, I think, isn't it? 6 and 13, yeah. So 6 and 13. So factors of 78 are 6 and 13, and they add to 19. But I want them to add to minus 19, so 2 minuses. If you can't factorize, go straight to minus b. All right, minus b will still give you the same answers as x equals 6 and x equals 13. So there's your two answers. Okay. Next one. Solve for x, log to the base 2 of x plus 1 minus log to the base 2 of x minus 1 equals 1. Now, check. Are the bases the same? Look at the left-hand side. Log to the base 2 of x plus 1 minus log to the base 2 of x minus 1. What is minus related to? Minus is related to division. So therefore, I can rewrite the left-hand side as the following. A single log to the base 2 of x plus 1 over x minus 1. All right, that's one of the rules in your tables. The difference between two logs with the same base is exactly the same as the log of their quotient, okay, or their fraction. And that is equal to 1. Now, log to the base 2 of something I don't know, that's a very difficult thing to solve. Let's see what this thing looks like if I turn it into index form. The base of the log on the left-hand side is 2. So the base of the index side will be 2. The log gives the power that will be over that 2, which is 1. And that therefore then is equal to x plus 1 over x minus 1. And all I've got to do now is clear the fraction. So you get 2 times x minus 1 is equal to x plus 1. 2x plus 2, sorry, 2x minus 2 I should say. I'm just beginning to see things now at this stage. So 2 times x is 2x, 2 minus 2 equals x plus 1. So that means you take x away from both sides, x. You're going to take 1 away from both sides, minus 3 equals 0. That gives me x equals 3. And there's your answer. So we're falling back on algebra. Chapters 1, 2, and 3 of the book. I told you they will appear everywhere. You got to remember how to do all your algebra. Okay. Solve for x. 4 times log to the base x of 2 equals log to the base 2 of x plus 3. Now, do you notice the biggest problem? The biggest problem here is that the bases are different. Okay? We're dealing here with an unknown base, and that's a very difficult thing to work with. So what I'm going to do is I'm going to take the left-hand side and I'm going to change it from an unknown base into a known base. And obviously, because log to the base 2 is over here, I want to get the left-hand side to match it. But just before I do that, coefficients of a log can also be written as powers of the number we're getting the log of. So in other words, 4 times log to the base x of 2 is exactly the same as log to the base x of 2 to the power of 4 equals log to the base 2 of x plus 3. Now, the bases are different, okay? So what I'm going to do is change the unknown base into base 2. So I'm going to change this side to base 2. Okay, so let's have a look and see what happens. You rewrite this log with the new base first of all. You're going to get a fraction. Every time you change the base, you get a fraction. So you rewrite this log as the same log with a new base. So log to the base 2 of 2 to the 4 over log to the base 2 of the old base, which was x. And that's equal to log to the base 2 of x plus 3. Okay. Log to the base 2 of 2 to the 4. You see it? The base on the log is the same as the base in the index, so that cancels with that and leaves you with 4 over log to the base 2 of x is equal to log to the base 2 of x plus 3. Okay, now here's the key thing. How do we work this out from here? How do we bring these two together? Now that they have the same logs, we're going to have to clear the fraction, okay? And in order to clear the fraction, let me just see very quickly what they do in your book. Yeah, okay. So in this one here, we're adding, they use the rules. I'm going to follow the way they do it in the book. They use the rules here of log to the base 2 of x plus 3. Okay. Now, log to the base 2 of x plus 3, you can take that as log to the base 2 of x plus log to the base 2 of 3. So what we're going to end up with, if we take, so log to the base 2 of x plus 3, take it equal to y, okay? We're going to set log to the base 2 of x equal to y, because I'm just thinking on the top of my head. You could also do it, you could just multiply across. So you could actually multiply across. I'm going to do it that way, actually. You could say, clear your fraction. This is what we do in algebra. Clear your fractions. So 4 over log to the base 2 of x equals log to the base 2 of x plus 3. Now what I'm going to do here is I'm simply going to let log to the base 2 of x equals y. I'm going to use substitution. Okay, so everywhere there's a log to the base 2 of x, you're going to call y. So 4 over y equals y plus 3. Much easier to deal with. Much, much easier to deal with. Now clear your fractions. I was going to clear the fraction back here, but I've actually just copped on to the fact that if I cleared my fraction here, I'd be multiplying two logs by one another, and I don't want to do that. Now you could keep the log and just add the parts of it, but instead what I'm going to do, because log to the base 2 of x is a difficult thing to deal with, I'm going to bring in substitution similar to the way I did with indices. And I'm simply going to say, okay, log to the base 2 of x, let log to the base 2 of x, that difficult thing to do, let it equal to y. Rewrite the equation, now clear your fractions. So I'm going to multiply every term by y. 4 equals y squared plus 3y. And straight away, you've got a quadratic. Y squared plus 3y minus 4 is equal to 0. That's it. So what does that give me? Open your brackets. Let's see what the two answers are. Y by y, 4 by 1. And you have to get minus 4. The difference is to be plus 3. So minus 4 plus 1. And that gives me two answers. Y equals minus 1. And the second answer, y equals 4. Okay. Now, y was only allowed to substitute. So I've got to go back over here. Let me write over here for you. Let y equals log to the base 2 of x. Now, take the first answer. Minus 1 equals log to the base 2 of x. And let's put it into index form and see what happens. Remember what I told you? The log is the power. Okay? The base of the log is the same as the base of the index. So if the base of the log is 2, then the base of the index form will be 2. The log is the power. So that's minus 1 equals x. Straight away, 1 over 2 equals x. And there's your first value. Now do the same with 4. So put 4 in for y. So that's your first case. Second case, 4 equals log to the base 2 of x. Again, go back to index form. The base of the log is going to be the same as the base of the index. The log is equal to the power 4, and that's equal to x. And 2 to the power of 4 is 16. So x is equal to 16. And that's my second answer. Okay? So therefore, we get a half and we get 16 as the values of x, which, thanks to y, are found by substitution. Okay, next one. Let me get rid of that. Solve the equation 2 to the 2x minus 8 times 2 to the x plus 15. Now, we met these before. Do you remember them in the indices? And the middle term in brackets, that 2 to the x, that has to be created here in the first term so that it becomes a common term in the first two, again, that I can use substitution with. So, if you remember what we did with indices, because 2x means 2 multiplied by x, and because multiplication is commutative, I could also write that down as 2x to the 2, and put a bracket between the x and the 2 like that. Minus 8, 2 to the x, plus 15 is equal to 0. Difficult. That's a difficult quadratic. So instead what I'm going to do, as I did in the previous part on indices, I'm going to let y stand in for 2 to the x. And I'm going to rewrite this quadratic, not in terms of 2 to the x, but in terms of y. So y squared minus 8y plus 15 is equal to 0. And again, straight away, you've got a quadratic that you can deal with. Y squared is y by y. Factors of 15 that add to minus 8. Well, minus 3 and minus 5. So y is equal to 3 and y is equal to 5. So there's your two values of y. But this question is not about y. This question is about x. Okay? So go over here and look at case number 1. Let y equal 2 to the x. So take 3. 3 equals 2 to the x. Now, if you wish, because it's an unknown power, you can go back into logarithmic form. All right? So I'm going to go back into logarithmic form. The base of the index is the same as the base of the log. See that? The log is the power, and therefore 3 is what I put in here. So there's your first answer. Don't even have to work out log to the base 2 of 3. Just leave it as log to the base 2 of 3. Perfectly fine. Secondly, what's the second one? 5. So 5 equals 2 to the x. And again, because it's an unknown power, just go back into logarithmic form. The base is 2. So this is log to the base 2. And again, what are we dealing with? The log is equal to the power. So it's equal to x log to the base 2 of 5. And that's your second answer. So your first answer is log to the base 2 of 3. And your second answer is log to the base 2 of 5. Okay. Now, once you've kind of mastered those processes, there are 3 different forms of logs that we have to be able to identify. And the first one we have been dealing with right the way through since the very beginning. That's when you have a log with a numerical base and a numerical subject. Okay, so when a and x are both numbers, like for example, log to the base 3 of 27. How many times would I multiply 3 by itself to get 27? And the answer is 3 times. Okay, But there are two others that we need to know how to recognize when we're doing these questions. And the first one, the first one we said already is a to the x, that's fine. This one here, log to the base 10 of x. Now, it's called the common log. How many times do I have to multiply 10 by itself to get a certain value? All right. But because it's so frequently and widely used, the shorthand way to write log to the base 10 of x is just log x. All right. So whenever you see log x in a question, I would suggest you always rewrite that as log to the base 10 of x, just to remind yourself what base you're using. Okay. And the second one is log to the base e of x. And again, that can be written in a disguise as ln of x. And ln of x is simply another way, it's called a natural log of x, but it's another way to write log to the base e. So my suggestion is this. If you have log x, rewrite it as log to the base 10 of x. If they give you ln of x, the natural log of x, rewrite it as log to the base e. Okay? Because once you have the base of the log, then you can apply the rules and the formulas. And by the way, the formulas and the rules of logarithms, they apply to all three forms. All right, they simply apply to all three forms. It doesn't matter, but as long as you have the base written, then you can apply the rules. So my advice would be log x, the common log, write it down as log to the base 10 of x. The natural log, ln of x, write it down as log to the base e of x. And don't be afraid to change before you apply the rules. Okay, now, why do I point out those three? And why are they so important? The answer is because they're on your calculator. There's log to the base a of x. That's the button that you use. It's in the same place on the old style calculator, but that's the button you use when you want to use a base with a number. So if you want to put in log to base 327, you tap that, you fill in the base 3, you fill in 27, you press equals, the answer will be 3. Okay? Log to the base 10 of x, where's that? Well, there it is on its own. That's an automatic log to the base 10. And finally, log to the base e. There it is. Logs get 3 buttons on your calculator. This one here, which is the numerical log. This one here, which is the common log to the base 10. And this one here, which is the natural log to the base e. So know where they are when you want to use them. If you want to just go straight into the answer, of course you can use them. If you want to transfer them into their respective bases and then apply the rules, that's fine too. Lastly then, if the base of the log and the base of the index match, they simply cancel. Now, what do I mean by that? Well, something like this. Log to the base 7 of 7 to the power of 3. There are 2 things on the left-hand side. There's a log with base 7, and there's also an index with base 7. So because the log is base 7 and the index is base 7, the log and its base, along with the base of the index, cancels, and the answer is simply the index, 3. What about this one? ln e to the 5 equals 5. Why? Because don't forget what the ln is. ln is log to the base e of e to the 5. Now, again, what do we notice? The base of the log and the base of the index are the same. Cancel them, and you get your answer of 5. Okay? So they are quite straightforward. Now, that's enough for me. I need you to go now and practice, and I want you to practice on these, page 188, page 189. Looks like a lot of questions. They're only single questions. They're quite easy to do. The very beginning are just manipulations. The ones on page 189 and the latter parts, page 188, are the little equations. But keep in mind the 3 most important rules. Number 1, be able to interchange between log form and index form. Okay, be able to know how to make that change over. Number 2, the change of base rule. If you want to change a base of a log, you will always build a fraction. You rewrite the log on the top of the new base, and then you use the log with the new base together with the old base as your denominator. And finally then, the one that we had a few minutes ago, if the base on the log and the base on the index are the same and they're being used together, you can cancel the log on its base and the base of the index and simply keep the index as your answer. So off you go with those questions now, and if you find you need help with these anyway along the way, just send me an email with the respective question and I'll get the solutions back.